That's happened to me multiple times, believe it or not, where you're in a scientific discussion and suddenly hear from the pocket of somebody says, I don't understand how to do that. And it's like, okay. So basically we have a period for the orbit. So here's t, okay? So that's gotta be 24 hours. Now, for scientific stuff, that is not a useful unit. Hour is kind of weird. So let's convert it to something useful. So that's 24 hours times 60 minutes per hour times 60 seconds per minute, right? So what we got here is 24 times 3,600 seconds. Oh boy. Like that. I'm not going to do this out. Okay, but that's how many seconds we're dealing with. Okay. So then, what else do we want to do? Okay, so we have an orbit. Here it is. So let's say this is the radius of the orbit, measured from the center of the Earth. So the circumference of the orbit is 2 pi r. Okay, and then as you go around the orbit, you have some speed v. Okay, so this is your distance that you have to cover. Okay, so you got to cover a distance of 2 pi r, and that's to go all the way around. You're moving at some speed v, and you have some time to do it in, which is t. Is that okay so far? But of course, v itself, we just calculated, right? In general, v orbit is equal to the square root of g m e over r, where r is the height above the center of the Earth. So you take this thing, you shove it in here, and you see what you get. So, bear with me here. Just want to make sure I'm in sync with what I did. So, t is d over v. That is true. Okay, so it's a bit busy, but only because there's a bunch of numbers floating around. So let me try to collect those numbers all in one place. Okay, so we know t is some random number, and this is d over v. So we have d is 2 pi r divided by t, that is whatever is over there, square root of g, mass of the Earth, divided by r. Well, sorry. This is meant to be v. This is meant to be v. I'm writing this equation. I miswrote it. So now we get 2 pi divided by this funny number, square root of g m e, times, r goes up, so this is like r to the 3 halves. Okay, so we know this, so we can get r, right? So we get r, and then, having obtained r, if I want to know the height above the Earth's surface, that is the distance from the center of the Earth minus the radius of the Earth. That's how high these things are above our heads. So you just have to like plug some numbers and have some fun. It's kind of an entertaining little exercise. But when you finish the exercise, what you discover is that the height is 36,000 kilometers. Remember, the Earth is 6,400 kilometers. This is like 10 times the distance, okay? So geostationary satellites are really, really, really high up. So this little innocent picture is completely wrong. Well, is it? Is that 10 radii? Maybe not. Maybe it should be here. That's how it comes out. Before I continue, I feel like I am killing you by talking about all this. Do you have any questions? Do you all know this stuff already? Is this covered somewhere? Okay, so yeah, this is the basic idea of how satellites work. Like where do you put them, how fast they have to go, how much energy you have to dump into them to get them up there. Yeah, go ahead.
Is this at all related to free fall?
Yes, so the satellites up in space are from their perspective, in free fall. So yes, they're just falling. The entire time they're just falling. They're active on the difference of gravity. They're in free fall. So like if you take another object and you're up in space and you're inside your little space habitat, you let it go, it's accelerating exactly the same way as you are. So from your point of view, it's not accelerating. Does that make sense? There's no air friction to slow it down.
Yeah.
The air is moving at the same speed too. It's inside your habitat. So things seem to be weightless. They're actually not. But in practice, it's as if they were weightless.
So that's how satellites stay in orbit, right?
That's how, good, the question is that how satellites stay in orbit. That's how astronauts seem to be in zero gravity. But that would be true even if they were moving much slower, and this was the situation. Let me show it to you. Here's the Earth. Well, no, I don't want to draw it this way. Here's the Earth. And imagine that the orbit, very unfortunately, looks like this. So this is not a healthy situation for the astronaut. Okay? But up until they enter the atmosphere and then meet their demise, I hope this doesn't happen. But if while you're free falling out in space, you're still free falling. So as far as you're concerned, you're in zero gravity inside your spacecraft. The entire time you're falling. The reason the atmosphere gets into the game is like once you hit the atmosphere, it starts slowing down rapidly. Then you feel it. Okay, but otherwise you're just free falling. Anything next to you is free falling. Like nothing exciting is happening. Okay. There's a bit too much calculus on this slide. Let me just blast past it just for a second, okay? And just tell you an important punchline, okay? Which is that the potential energy of gravity can be written like that. Okay, so how do you see that this makes any kind of sense? Okay. So instead of deriving it, which is what's on the previous slide and will be visible on Canvas after this lecture, let me show you why the final result makes sense, and then you can derive it for yourself using calculus if you feel like it. So the potential energy of gravity, which is usually written as U of gravity, is minus G M1 M2 over R. Okay, so why does this make any sense? So if, imagine you first make R, this R, go to infinity. If R goes to infinity, the potential energy of gravity eventually drops to infinity. If you draw a picture of this, here's R, here is U. This basically says, because of the minus sign, that's why this thing is going like that. You want to go down the slope, right? You want to go down towards the lowest potential energy. This says that the lowest potential energy is when you go all the way down to the object that's attracting you. So the minus sign is so that gravity is attractive. Next, another reason why this is sensible is that it better be the case that U of G is approximately equal to mgh, right? Now that does not look like that at all. So how are they related? Well, let's write the distance between the objects as the radius of the Earth plus h. Let's write m1 as mass of the Earth, and let's write m2 as the mass of an object. So what are we going to get? We're going to get the UG is going to be equal to minus G, mass of the earth, mass of the object, divided by RE plus H. Okay, so this thing is GME over RE times M, sorry, like this. Why am I hesitating? Sorry. H over RE, like that. So I just pulled out RE. This thing is the acceleration of gravity G that we've met before. So what's left is this business. So now there's a trick. 1 over 1 plus x in math class, if x is small, can be written as 1 minus x plus dot 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 dot. That's called the Taylor series. So it's a good approximation to replace that with this, as long as x is small. So what we get, oops, sorry, I lied. 1 second. I almost lied. 1 second, let's get it right. We get G ME over RE times M plus okay, so I'm sorry. This thing is G, so there we go, MGH. And this thing is a constant. It's independent of H. So back when we were writing these formulas, there's always a plus a constant here. So you might wonder, what's the constant? Well, there it is. Okay? So it all fits together. I'm out of time, so I should shut up. But